Okay, if you're tuned in tonight's video, if you could just type your name in the live chat there so I can see who's here, and then we'll go ahead and get started in just about a minute. If you hear any crazy background noise, please excuse it. I am currently sitting in the closed cafeteria of a college campus, so there's a little bit of chatter going on. Okay, we're going to go ahead and get started. So tonight we're going to be covering Chapter 4, Glacial Landscapes. Okay. First we want to start with defining what glaciers are. So a glacier is a thick mass of slow-moving ice, typically a composite of ice and rock, that originates on land, either from the accumulation and compaction or recrystallization of snow. These are dynamic agents of erosion. They are actually one of the primary erosive drivers on the continental mass and are part of both the hydrosphere and the lithosphere. Glaciers are presently found on high mountains or at high latitudes in both the northern and southern hemispheres of the Earth. Glaciers have been, are, and will continue to be major agents of landscape formation and change. When we talk about glaciers, there are actually two major types of glaciers that we'll refer to. The first are the ones that you're probably more familiar with. These are the valley or alpine glaciers. These are the ones that exist in mountainous areas and tend to flow down a valley from an accumulation center. So Glacier National Park is a region with a number of valley glaciers. Some of the more popular ones up in Banff in Canada, up by Lake Louisa, these are alpine glaciers. Ice sheets are actually considered glaciers. These are continental glaciers. These are a much larger scale than valley glaciers. So valley glaciers are a regional scale. Ice sheets are a continental scale glacier. On ice sheets, the ice actually flows outward in all directions from one or more snow accumulation centers. So the snow tends to accumulate in a region and then flow outwards equally in all directions. In present day, Antarctica and Greenland are the only continental ice sheets that currently exist. Most people tend to assume that glaciers just move by kind of sliding down the Earth's surface. They actually move in a very complex mannerism that is typically broken down into two major processes. Okay, the first is called the plastic flow. This is where the ice actually flows internally, where the pressure of the ice exceeds a certain level, and instead of breaking apart, the ice kind of acts like silly putty or taffy, where it actually rolls over itself as it moves. This typically occurs in the deeper regions of the glacier, below 50 meters into the glacier from the surface. Above this depth, glaciers are still very brittle, and they tend to crack as they move, creating the crevasses that you hear about on the news. So those big giant openings within a glacier. That's the brittle section of a glacier. If you go down deeper below these crevasses, that's where you start to enter the really ductile or plastic movement. The second way that glaciers move is through basal slip. This is what most people commonly think of when they talk about a glacier movement. This is where the entire mass of ice actually slides along the ground, along the base of the glacier. What happens is the glacier typically builds up enough pressure that you actually get a very thin sheet of water that develops between the Earth's surface and the glacier, and a glacier will slide along that sheet of water. This image is just looking at a cross-section of a typical glacier. So this is just showing you, in an alpine glacier, you've got the valley wall, which is confining your glacier and directing its flow. So it's channeling its flow into a single direction. This is showing you the flow of ice. So you have higher velocities in the center of a glacier with lower velocities on the outer edges. This is due to the friction of the friction of the contact between the sheet of ice and these valley walls. So rubbing up against that rock really decreases its velocity. So glaciers have a much higher velocity in the center and lower velocities out along the edges where it's coming into contact with the valley walls. And then here it's just showing the brittle zone at a depth of about 50 meters retreat, or it'll look like your glacier is actually shrinking backwards. So this is just showing you the difference between your zone of accumulation and your zone of wastage. So you have your zone of accumulation, typically at your higher elevations or latitudes where you get your snowfall, you get higher amounts of snowfall through longer periods of the year. And as you get this snowfall, it starts to move downslope or down gradient. And as it does this, it starts to enter warmer temperatures, warmer regions where you start to get snow melt. And you have glacial progression if this rate of melting down here is lower than the rate of snowfall up here. So when you're looking, here's your direction of the ice movement. Down at the bottom of the glacier, you tend to get glacial lakes that form. And as the toe of the glacier starts to melt, you'll get large pieces of the glacier falling off through a process called capping, and this is where you get these large icebergs within these glacial lakes. So what does it mean when a glacier is stationary? Okay, so we're talking about accumulation and ablation or wastage. So when it's stationary, it does not mean the glacier is not moving. Okay, and if a glacier is stationary, then accumulation is not exceeding wastage, because if you had more accumulation than wastage, then you're going to have a glacier advancing. And if your accumulation is less than wastage, you're going to have a glacier retreating. So if you have a rate of accumulation that is equal to the rate of wastage, then you get a glacier that is quote-unquote stationary, or it's not advancing and it's not retreating. There's still movement of ice from the accumulation area to the wastage area, but that rate is equal all the way through the glacier. I'm going to post a link to this video on the class site this evening. So this is a glacial retreat and calving in the Atlantic Ocean. It's really just a 4.5 minute video of watching very large pieces of a glacier fall into the ocean. I mean, it's kind of cool to watch. You get some really massive waves. So this is an image of basically the last piece of a glacier remnant in Alberta, Canada. So this is a receding glacier up in Alberta, Canada. This glacier has almost entirely receded or undergone wastage due to the global climate change occurring. So like I mentioned, glaciers are a major erosive agent. They are one of the primary drivers right behind water. Glaciers are capable of large amounts of erosion and sediment transport. Glaciers erode the land in two primary manners: plucking or lifting of rocks. And this is where rocks that have already been plucked and are suspended within the ice actually act like sandpaper and polish the surface below them. So we talked about the basal slip, so the glacier is still moving down. And as it does that, all the little rocks that are inside it actually scour the earth beneath them like sandpaper, and can either create rock flour, which is where they pulverize the rock below so finely that it is a powder-like substance, or you can get glacial striations, which are grooves in the bedrock typically carved by larger rock fragments as they are pulled along. So this picture here is an example of glacial striations that were created by a glacier, and they show the direction of ice movement. So you can see here, assuming this picture is oriented north and south, you had glacial movement from the northwest to southeast. This is Peyote Lake in Banff, Alberta. If you've ever seen pictures of glacial lakes, you'll notice that they are this very vibrant blue color, and they look exactly like that in real life. They are just this gorgeous turquoise. They get this color because glacial rock flour is pulverized so finely that it never settles out of the water column. And so this rock flour that's suspended within the water reflects the light in such a way that it gives us this blue shade. So you get a lake developing, and the sediment tends to settle out and rest on the bottom of the lake. That does not happen with glacial flour. It's always in the water column and reflecting the light in such a way that it gives this crazy shade to the lake surface. Glaciers are unique in that they can carry large amounts of sediments in all grain sizes. Sediment produced by grinding and plucking action of the glaciers on rocks the glaciers travel over are carried within the glacier column miles and miles away. So if we look here, this is at the toe of a glacier, and you can see you've got these cobbles down here and what looks like really fine-grained clays or sands and much larger rocks here. Glaciers are the only agent that is able to continuously carry any sediment size. So how are sediments deposited by rivers different from those deposited by glaciers? So think back to your last chapter. The type of sediment that a river could carry was dependent on the velocity, whereas a glacier, it is dependent on what it encounters and picks up. So if you read through your options, sediments deposited by rivers are more weathered, so that's probably not true. They undergo different weathering process, but it doesn't mean that one is more than the other. Sediments deposited by glaciers tend to be transported further than those deposited by rivers. This is possible, but glaciers, especially in current days, really don't have the same extent as like the Mississippi River. There's no glacier that has a depositional region that large. Sediments deposited by glaciers tend to be unsorted and contain many particle sizes. Okay, so glaciers are able to pick up any grain, no matter what size it is, and carry it along. Or rivers are more likely to transport and deposit very large sediment sizes. So like we talked about last week, rivers have to have very high energy to carry large sediment sizes, and they really only have that high energy during flood events or significant discharge events. They don't last very long, and those tend to settle out first. So our correct answer here would be C. Sediment deposited by glaciers tend to be unsorted and contain many particle sizes. Okay. Here we go. So glacial erosion and deposition actually creates many unique landforms. So this is looking at how glaciers will impact a landform over time. So assume you start with an unglaciated topography. There's never been a glacier here. You have a V-shaped valley that your stream has eroded, like we talked about last week. And then you get a regional cooling. We start to have a glacier begin up here and advance down into the valley. Now, as that glacier advances, it starts scouring the edges and creating this main glacier. Now, you notice these little valleys up here, they actually create what are called tributary glaciers. So there'll be these smaller glacial activities that start up in the mountainous areas. These glaciers create a variety of unique landforms within these ridges or mountain systems. So you get reats, which are these high ridges between two glaciers. So they get these very sharp very abrupt points. You develop what are called cirques. Cirques are actually this large bowl formation. This is where a glacier tends to originate because you start to get an accumulation of snow and ice in this region. They're partially shaded because of their shape. They're in the higher regions, and because of the bowl shape of it, you get a lot of snow and ice settling straight down in it before it starts to accumulate over the side and down the valley. Then once that glacier retreats, you've gone from this unglaciated V-shaped valley to this very deep U-shaped glacial valley that has, you see as it comes down, it erodes the landform underneath these tributary glaciers. So those actually terminated at the top of this glacier, so they never eroded down quite as far. So you create what are called hanging valleys, so these very abrupt cliffs. So here's a hanging valley, and this is actually where you get a lot of waterfalls in formerly glaciated areas. So this is looking at a U-shaped valley, glacial valley in Alberta, Canada. So this is a really typical landform that you would see in a formerly glaciated region. Those very gentle side valleys with a very flat, even valley bottom, as opposed to the river-incised valleys, which has a very steep, abrupt sides and a very narrow valley bottom. So a cirque, like I said, is that amphitheater-shaped basin that is typically the origination of glaciers. And here's a, whoops, sorry about that, guys. Here's a collection of cirques near Alberta, Canada. A horn, which I did not mention before, is actually a pyramid-like peak. The Matterhorn in Switzerland is one. So a horn is when you have arites, which are these narrow ridge separating valleys, and they come together, and they actually create this peak at the intersection of two arete regions. You also develop what are called tarns. These are pools or lakes that form in the cirques after the glacial retreat. So in formerly glaciated areas, you'll get the last remnants of that precipitation retained within these basins, and that's what forms a tarn. And here we have an example of a hanging valley. So we have our ice movement is down in this direction. Now the ice has begun retreating. See, this whole valley has already retreated and the glacier has cleared out. But you still have a bit of a regional glacier, or a tributary glacier here. You've got the hanging valley where it met up with the original main glacier. Another landform are fjords. Okay, so the fjords of Norway are actually long U-shaped valleys that were eroded by glaciers. And what happens is as these glaciers melt and retreat, they actually fill up with seawater, giving them their salty or brackish composition. They form from erosion caused by the valley glaciers where the coastlines are extremely mountainous and are typically found in Greenland, Norway, British Columbia, Chile, and New Zealand. Okay, there is actually one fjord in the state of New York, and if you are able to name that fjord and email it to me, I will give you 2 points of extra credit. Okay, so we've talked about glacial erosive features. Now let's talk about some of the glacial depositional features we find. So first we want to talk about the sediments from glacial depositional activity. So glacial deposits are called drift, and glacial drift is divided into 2 types. The first type is till, which is where, as the ice melts, every sediment that is entrained within that ice is just dropped out, unsorted, just immediately. It's all suspended in the ice, and it's like the ice just disappears and it just goes straight down. The second is stratified drift. This is where the deposits are sorted by size and weight by running meltwaters into layers. We can also get glacial deposits called loess. These are wind-blown silt sediments. They're typically a yellow to brown color. They're very thick and easily erodible. Oh, sorry. These are sourced from terminal glacial deposits. Now, terminal glacial deposits are sediment deposits from the furthermost portion that the glacier has ever extended. And the thickest deposits that we have found are currently in the U.S. and in China. China especially, where they can be up to 300 feet deep. Okay, so this image here is just showing you the Laurentide ice sheet, which was the most recent glacial period. And this is the furthest extent down into the United States that this ice sheet progressed. And here you're seeing the loess fields. So you have wind-blown paleo winds, or the loess blown by the paleo winds. And so as it blows off of these terminal regions of the ice sheet, it deposited across the Midwest of the United States. Some common landforms made of glacial till are moraines. These are layers or ridges of till. So you have your lateral moraines. These are till deposits that develop along the edges of the glacier, along the valley walls. You have medial moraines. These develop when two glaciers actually come together before forming one down gradient. You have your end moraine, which is deposits that occur as the glacier undergoes wastage, and the sediments that are at the toe of the glacier are then deposited. So your lateral moraines, here's an example of a lateral moraine where you just get that deposition alongside the valley wall between the glacier and the valley, or glacier and the wall. And then your end or terminal moraine. These develop at the furthest point the glacier reaches. And here's another image of a lateral moraine. So we're actually able to use these end moraines to determine how far ice sheet the most recent glaciation period is extended. The reason we can only do it for the most recent glacial period, though, is because previous glacial periods did not extend as far. So as a glacier advances over those earlier end moraines, it actually reincorporates all that sediment into it before depositing it into new glacial formations. So evidence of most earlier glacial activity has actually been destroyed by the most recent event. Okay, like I said, a medial moraine occurs along the center where two glacial streams meet. So right here would be a medial moraine. And then a ground moraine. This is the till underneath the ice that is spread out in gently rolling landscapes where it fills in lower areas. Several Midwest states are overlain by glacial till, resulting in its relatively flat topography, such as northern Illinois, Indiana, and Ohio. I got my bachelor's degree in geology in Ohio, and I can tell you right now that if you are not interested in glacial till, it is the most boring geology known to man, because they're not joking. It is super flat. It's thick layers of glacial till overlying the entire area. It's really not exciting if you don't like glacial geology. But if you do, go check it out. They're pretty cool. Ohio is full of these end moraines and lateral moraines. Like their water theme park out there is named Splash Moraine. So I was talking about the extent of the glacial periods. So when we talk about the most recent event, the most recent was the Wisconsin age. And these are all end moraines from glacial activity in the Wisconsin age. Now, there are some evidence of the immediately preceding glacial age, the Illinoisan. The only place that these end moraines exist is in western and southwestern Illinois. Every other area that was impacted by that glacial event has been reconstituted by the Wisconsin age. So the only evidence we have of that previous glacial activity is right here in Illinois. There we go. Yeah, so Jamestown is right here, right at the kind of easternmost reach of the Wisconsin age glacial end moraines. If you go out near Fredonia, I think it's called Overlook Park or Oversight Park, out near Fredonia. It's this very large hill. It's got a little park on it, and if you go up there, you actually look out across Lake Erie. You're actually on top of this end moraine right here that exists. So if you ever get a chance and you're bored, go check out that park. Go check out that end moraine. It's pretty cool how you don't even realize that some of these landforms that exist in the area are actually things that you're studying in class. Yay, making it applicable. Okay, moving on. The deposition of these moraines actually resulted in major changes to North American watersheds after the Ice Age because they created divides and altered the directions rivers could flow. So you see all these end moraines actually had a huge impact. So some of the Great Lakes were actually bounded by these end moraines and unable to continue flowing southward. Changed the route of a lot of rivers because of these end moraines blocking them off. So this is just looking at some more glacial deposits. You have a retreating glacial here. So the furthest most extent of this glacier would have been about right here, where you have your end moraine. As that glacier starts to retreat, you get this slow buildup of sediment deposits here. And at some point, the glacier kind of stalled in its retreat and built up another end moraine here. You have a development of a kettle lake, which we will talk about in a few minutes. You have kames, which are, so kettle lakes are negative landform creations by glaciers, whereas kames are positive landforms. Eskers are another positive landform, and then drumlin fields. So first are drumlins. So drumlins are elongated parallel hills, so they exist typically in clusters, and they all lie parallel to one another. And they have a steep side, otherwise known as the blunt end. So this right here, where it's a much steeper hill, but it's a very rounded portion. And then your pointed end, or your tapered end. So your blunt end faces the direction the ice came from. Okay, so if we're looking at this, if your blunt end is here and your tapered end is here, then the ice was flowing from this direction to that direction. Like I said, these typically occur in clusters called drumlin fields. There's actually a very large cluster of drumlin fields up near Rochester, I think, which is pretty cool. It's most obvious on topographic maps, but there are some areas where you can really see these drumlins very clearly. So looking at this drumlin, what direction did the glaciers move in this landscape? Did it move right to left or left to right? Okay, it moved right to left because the blunt end is here and then the tapered end is down here. Kettle lakes are formed when chunks of ice become lodged in the ground and later melt. So we talked about those icebergs calving off of the end of a glacier. So as they break off, they implant down in the ground, so they create a depression, and then as they remain in place, they begin to melt. And the depressions they've created now become these lakes that form. Bear Lake up near Cassadaga is a kettle lake. So if you've been to Bear Lake, or if you know Bear Lake, you can see just like the scale of how big these icebergs were that calved off and created them, because it's not a small lake. Okay, some deposits from stratified drift. The first one is outwash plain. So these are very broad ramp-like surfaces that are composed of stratified drift deposited by meltwater. So we talked about the stratified drift is where you actually get the layering of the sediment sizes based on meltwater movement. So this is an example of one. And then the meltwater, as it flows across this broad area away from a retreating glacier, see there's our glacier, and here's the water coming out. As it moves through here, it actually begins to take on a braided river mannerisms. Another type of stratified drift are eskers. And these are sand and gravel ridges that are actually formed when streams of meltwater develop within tunnels within the glacier. So they're actually moving within and underneath the glacier, and as this water is flowing out, it's depositing any of that sediment that has melted out with it along these very long, sinuous kind of paths. There are a few, again, up by the end moraines up near Fredonia. They're a lot harder to find. I only know of one really good area, and that's on private property. I don't know if there's any more evidence of eskers up there that are accessible to the public. Okay, a kame is a steep hill of sand and gravel that forms within the ice. So this is a region where sand and gravel is actually deposited in a very large portion within the ice. Typically what would happen is if you get a crevasse or an opening straight through the glacier down to the Earth's surface, you have water rushing off down into that hole and hitting there. And as it hits there, it deposits a large portion of sediment before continuing to run off. And this is where you get the development of cames. Again, I'll post the link to this video, how eskers and cames form. Okay, like I mentioned, there is a second type of glacier. This is the continental glacier, or the ice sheet. Oops, sorry guys. They're very similar in the kind of deposits they create. Proglacial lakes, which are lakes that are trapped behind an end moraine between the toe of a glacier and the end moraine. Here are evidence of eskers, a sinking stream, so you get a came developing inside here. So effects of the Ice Age glaciers. During the last glacial maximum, it occurred about 18,000 years ago. Sea level was almost 100 meters lower than it is today. So this is showing where the coastline was 18,000 years ago during the last glacial maximum. 18,000 years ago, the last glacial maximum, the continental ice sheets and the alpine and valley glaciers covered 30% of the Earth's surface. The ice that covered western New York was actually up to a mile thick. And like I said, if you're able to go check out that end moraine out near Fredonia, it'll give you an idea of how high that hill is. And that was all just sediment that was deposited out of a glacier. So to understand how tall that glacier must have been to form that land formation. The last glacial maximum was the last of many glacial periods that began approximately 2 ago. So when we talk about this, and we talk glacial periods, we are currently in what is called an interglacial period, so a period of warming with very little glacial activity occurring on our surface currently. The Ice Age is very complex and is difficult to pinpoint to individual causes, but most likely are caused by the changes in amount of solar radiation that reaches the Earth. These changes are caused by changes in the Earth's orbit, orbital shape, and rotational angle, also known as the Milankovitch cycles. So the Milankovitch cycles discuss the changes in Earth's orbit around the Sun, or its eccentricity. That talks about where it goes from more circular to more elliptical and back. Shifts in the tilt of the axis, or its obliquity, and then wobbling of the Earth's axis, or its precession, so how much it wobbles back and forth during its rotation. So our Earth's eccentricity has a cycle of about 100,000 to 400,000 years, where it changes back and forth. Obliquity is about a 40,000 year cycle, and precession is about 19 to 24,000 years. Another cause could be changes in ocean and atmospheric circulation patterns due to changes in the position of the continents and ocean basins because of plate tectonic movements. So as the plates move, it shifts the orientation of continental land masses and the ocean circulations, so the movement of the warmer and cooler airs and waters is significantly impacted, which can actually cause global scale warming and cooling periods. It's thought that the latest ice age may have actually been triggered by the formation of a land bridge between North and South America, so down here, which changed the circulation patterns between the Atlantic and Pacific Oceans. So the thought is that you used to have a weak current going up from South America through the Gulf of Mexico, with some of the current going into the Pacific Ocean and the warmer Pacific water coming into the Atlantic here. Once this formed, it cut off the warmer water that was coming into the Atlantic, and it cut off the cooler water coming into the Pacific, giving you a stronger northward flow of water and giving you more ocean heat released into the atmosphere. Okay, sorry, got that backwards. Cut off the warm water into the Pacific and the cool water into the Atlantic, giving you that warm northward flow of water into the northern Atlantic. of varying concentrations of CO2 with the ice age actually correlate with decreased amounts of CO2 in the atmosphere. So scientists are actually able to take ice cores that give you the concentrations of CO2 in the atmosphere, CO2 within the actual glacier, and give you an idea of higher temperatures and higher CO2 concentrations and lower temperatures or glacial retreats and lower temperatures and periods of glacial advance and lower CO2 concentrations. Volcanic eruptions can also trigger complex changes. They can both cool and heat the Earth's atmosphere, really depending on how they interact. And the role of volcanoes in ice age initiations is still actually very highly controversial within the science community. Okay, so this is just showing ice ages through the time. So we have a drop in temperature here giving you an ice age, and then an interglacial period of some warming, and then an ice age, and then a significantly long period of warming, and then a very brief ice age occurring. So the ice ages tend to last they don't last nearly as long as the interglacial warmer periods. And then there was an ice age occurring about 3 million years ago. The last glacial maximum wasn't actually a full ice age. And so here we are today where we're actually at lower temperatures globally than have occurred in the past. Oops. And then this is just a zoomed in look of glacial and interglacial cycles over the last 450,000 years. So you have your warming periods, your interglacial periods, and then your glacial. And so you can see here we're in an interglacial period right now, with slightly higher than average temperatures. Average temperatures of glacial and interglacial are probably right about 25 to 27. We're sitting at about 32. This is a chart showing global temperatures and CO2 that have been deduced from ice cores. So this is just showing the temperature change, so periods of high temperature, I think. Yes. And the chart shows a long-term pattern and short-term fluctuations of temperature of more than 15 degrees within a few decades. So short-term rapid rises and drops have occurred 24 times in the last 100,000 years. So just here, we've had 24 rapid rise and then drop, rise, drop, that. This is looking at climate changes of the past 12,000 years. So the end of the last glacial period was about 12,000 years ago, and then we started to see a gradual warming. And then we had just a cycling around 15 degrees Celsius. You start to get the Holocene climate optimum, which was a warming period, and then you get what was called the Little Ice Age, or period of cooling. You have your second Holocene climate optimum cooling period. You have human migration actually occurring here, probably because of ice bridges that developed between continents. Oh, I'm sorry, the Little Ice Age is over here. Pay no attention to me. So you have two periods of the Holocene climate optimum with a temperature drop. You have the medieval warm period and the Little Ice Age that occurred following that. This is actually a period, if I remember correctly, and you all definitely correct me if I'm wrong, but there was actually a period here where parts of Europe, according to historians, were covered with snow for an entire year. So that's what historians have deemed the Little Ice Age, a period of a very abrupt global temperature drop. So which of the following statements is true about the last ice age? Ice covered 30% of Earth's land area. There is twice as much ice in South America as compared to North. Oh, sorry. Oh. It was unique in that it was characterized by one major ice advance, or that all of the evidence about the last ice age comes from land-based glacial deposits. So the correct answer here is that ice covered about 30% of Earth's land area. Okay, we still get evidence about the last ice age from cores taken from currently existing glaciers and continental ice sheets such as Antarctica and Greenland. And this is just jokes, cavemen, see a little flower sprouting, and the ice age is ending. So they obviously must have been doing something to cause a global temperature increase. So, okay, so that is it for glaciers. I am going to post just some slides for an extra lecture that is typically done on just New York glaciers. It's not going to be graded. There's not going to be any homework for it. It's not going to be on your test. But if you wanted to learn more about New York State during the last glacial period, go ahead and take a look. I'll get that uploaded this week. In the meantime, you have your Mastering Geology assignment. Make sure you log in and do that. And you have your discussion board. So make sure you log on and contribute to that. That is it for this week. You have your exam in 2 weeks. Okay, so just briefly, your exam in 2 weeks, it is going to be open for 48 hours. It's going to open Monday morning, and it will be open until Wednesday morning. You want to take the exam first. Once you do that, you will do your week lessons for that. So I will be doing the live stream for that week. So week 7 live stream will be Wednesday evening instead of Monday evening. I'll repeat that next week, and I'll send out an email, but just be prepared for that. Your exam is going to be in the first 2 days of the week. Other than that, if anyone watching does not have any questions, I am going to go ahead and end this. And like I said, feel free to email me if you have any questions or issues. I think we've worked out all the Google Earth homework assignments.